I'm going to talk about our work in Osaka University. We are working on how to transfer human demonstration to robots using TMP. First, I would like to talk about the motivation. The motivation is you all know about that in industrial robots. When we teach the robot, we have to use teaching pendants or direct drive, or maybe we have a virtual environment. You can do that in virtual environments like ABB Rapid. But all of them, no matter which one we use, they are not applicable to a different robot. Once we teach the trajectory, it's only applicable to the same robot. Also, it's not applicable to new objects or various objects. To solve this problem, in industry, we have already seen lots of practical systems which combines vision to recognize the objects and then use motion planning to pick and place the objects. It's already very popular in industry, and there are several companies are working on this. But those applications are still pick and place. I would say it's still simple. Our goal in Osaka University is to solve more real or general tasks. That is tasks like assembly. We developed a system made of 4 components. Here's an overview of those 4 components. To the left side is a demonstration system. We call it a demonstration instead of teaching because we are demonstrating the task in front of interface. And then in the top right corner is the vision component. And the vision component recognizes the objects. And then in the middle is the familiar combined task and motion planning component. We plan the graphs, plan the task level sequences. We build a graph, search the graph, and find the motion. And then at the bottom is the false component. That is when we execute the planned results, we will do vision feedback, false feedback to make sure the planned motion can be executed correctly. And in the process, we have a bunch of data. During the planning, we plan the graphs. And during the placements, maybe there is a placements plan. And all of those data will be saved in a database. And we are using a relational database because we have the relation between hand and object. And we have the relation between an object and a fixture. And also we have a relation between a robot and a hand. We use a relational database to save the data as well as their relations. And after that, we can reuse the data. We can load the data from the relational database, considering the arm and the specific hand, and also the object. We can combine them and build a new graph for different objects and different hands and different arms. And this page shows the scale of our system. We saved 10,000 of graphs and they load them into the graph to build a graph like this. If we enclose the graphs, we can see each node over there. And also for different objects, we can load the data and combine them and build different graphs. And robots can search the graph to finish familiar tasks like flipping or reorienting this object. And for the upper robot, it's the next stage robot. When reorientating the object, it uses one pick and place, one regrasp, I'll say. And for the lower one, there are several regrasps, and depending on the different arms, but they have the same hands actually. That is the basic structure of the system I would like to talk. And based on the system, we developed several robotic applications. And next, I'm going to talk about the applications. The first one demonstrates the demonstration to the demonstration system and how to transfer them to the human. For example, here is the demonstration interface, and this student is demonstrating how to pile up 3 boxes. And he registers each boxes sequentially, the first, the second, the third. And then these boxes are saved in the demonstration system. And then the demonstration system will send the information to a planning system. In the far end, that's the demonstration system. And in the near end is the planning system. The planning system receives the demonstrated results. We only record the relative poses between the objects. And then the planning system will analyze the relative poses, determine the assembly sequence or placement sequence, and then automatically plan the grasps of this suction cup tool, and then determine how to pick up each object, determines whether it needs to regrasp or all of those things. We are familiar with that. Is about the combined task and motion planning. And finally, we got the robot sequences. And then we will send the sequences to the real robot for execution. And in the next video, I show several working examples, real world examples. First is to pile up 3 domino blocks. And according to the combined task and motion planning, the robot will determine to use a handover or not. In this case, the robot is doing handover, and for example, in this case, it's doing 2 times of handover to make sure the suction cup tool is correctly oriented, so that the robot can use it to reach the wooden blocks. And then there is another example, is to pile up 2 Coke cans. And for the first object, probably it's near to the right arm. The robot directly picked it up and placed down without using handover. But for the second one, the robot is doing handover to pick the object, and then doing handover again to move the object back and pile it up onto the first can. This is the tissue boxes, which we have already seen from the demonstration. And the robot picked and placed the first object without regrasp. And for the second object, it did a regrasp to move it back. And for the third one, it uses regrasp to change the pose of the suction cup tool and then pick up the object, and then use regrasp, use handover again to move it back. And in the first demonstration, we have shown a whole flow of the system from demonstration to automatic transformation. But the demonstration is simple, I would say. All of the motion are pick and place, are linear. And in the real world, there are some tasks like this. You need skills to install that. This is like a window of a cabinet. You have to go upward and then move backward to install it. We call this task is a skillful task, and we cannot plan the linear motion directly or using the combined task and the motion planning. Thus, instead of directly planning the motion, we record the whole trajectory, and then the planner plans the motion to the key or pivoting points of the skillful trajectory to realize the skillful motion. And here's a third example. In this case, I'm teaching a robot to fasten bolts. Essentially, I'm teaching the robot to the order of the fastening. For example, first I tell the robot to fasten the bolt in this place, and the robot has a camera in its hand. It's watching the goalpost of the tool. Then I told the robot to fasten the bolt in the second place. This is an enclosed, a zoomed up wheel. And then this is the second bolt. And after that, the robot received the first go, the second go. And then I'm going to drop the tool in front of the robot. The robot is going to recognize the tool again, find its initial position, and then plan the motion sequence and motion trajectories between the initial position and the two goal positions. And you can see that when the robot goes to the second boat, it's going to do a regrasp to move the tool to there. Probably they cannot directly go there because of some constraints. And then it's the execution. During the execution, the robot has to, you have already found that those boats are very small. So the robot has to include some feedbacks. Here we are using the 6 degree of freedom FT sensors installed and the wrist. Also here is also a big difference from the hole. The robot is doing spiral search and then impedance control to make sure the boat is correctly inserted into the hole. And after detecting the position of the boat is correctly inserted in the hole, the robot is going to fasten it. And then it's going to pick the second boat and move the tool to the second installation pose. And here the robot is also using the false detection to make sure there is a reaction from the boat and confirm the boat is already picked up. And then it uses the planned regrasp, the planned handover to change the pose of the tool and move it to the second goal. Also here is a difference. That's the error during the regrasps. And the robot has to use the feedbacks to make sure the boats can be correctly installed. This video shows the grasp during the used during the planning. We developed a grasp planner. The grasp planner will automatically generate the grasps for the objects. Here, for example, is to assemble 2 plastic parts, and then we plan the grasps for each of those objects. And then the robot will select the grasps from the planned grasp set, and then use that grasp to pick up objects and do the assembly. Here is the second one, is a screwdriver. Also, we have the CAD model. We use the CAD model to automatically plan the grasps, and then the robot will use one of the planned grasps to pick up the objects. Also, we can automatically plan the handover. We plan the grasp for each of the hand, and then determine if those 2 hands can grasp the object simultaneously. And then the robot will generate the handover motion considering the simultaneous grasps from both the hands. We can also do heterogeneous planning. The right part is the right hand has a suction cup and the left hand has a gripper. And then we can do them together, plan them together, and then realize the handover motion. Also, during the transfer between the human demonstration and the robot execution, we need to consider lots of constraints. For example, the gravitational constraints, while the assembled objects may drop if we didn't consider about that. And I'm going to go quickly to the second one. Here, I'm asking the robot to place some objects onto a plate. And I can set up the friction coefficient for the plate. If the coefficient is large, and you can see I attached a rubber surface onto the plate. And then the robot will tilt the plate to facilitate itself. And if the friction is low, I remove the rubber surface. And then the robot will try to keep the plate as horizontal as possible to make sure the objects will never slip out of the plate. And we also found some interesting results, like when the robot is going to place the second object, the right arm will move back a bit. And then for the third one, the robot will move forward a bit. And all of them was automatically decided by the combined task and motion planning. And also, we applied the system to a humanoid robot. And when there's a humanoid robot, it's different from a general manipulator because the base is not fixed. And when we plan the motion for the arms, we have to consider about the stability. We use a simple constraint here, that is the center of mass constraint. And then we compare the planned results. And after considering the stability of the whole body, the robot will generate different motion and avoid some of the dangerous handover motions. And here are two successful handover motions generated. And this is the second one. And in the third place, I'm going to show a failure case. And in this case, the constraints was not well considered, and then the robot fails. Also, we can determine, the robot can determine whether it need a second arm or not. For example, here we are trying to assemble some blocks, and especially for this one, and you can see the second and first object are not stable. But after the third, the proper object is placed on top of them, they become stable. But before we placing down the third object, we have to make sure the first and second object are already stabilized there. So we can use a second arm for the robot to stabilize the finished component. And then here are some of the examples. So the robot will install the second object, and then it's holding the finished part there, and then use the left arm to assemble the third object. And afterwards, all of them became stable. We can release both of the hands. And here is a more complicated example, I guess. Yes. We are also using pick and place and regrasp here to make sure those things can be stable. For the first object, we directly place it down there. And then for the second object, I guess it was not stable. So the robot discovered that it should hold the second object there to make sure the structure can be stabilized. And for the third object, the robot is doing regrasp and changing the pose of the third object, and finally install it to the third position. And after that, the robot knows the structure is stabilized, and then the last one just pick and place it there. And here's another example we developed together with a Bio Institute in Japan. The goal is to automatically arrange the tubes. And in that institute, they detect virus for around 100,000 copies, samples one day. And then there are lots of tubes. The test tubes, arranging the test tubes is a headache. They wonder if a robot could do that. And we found that this is a perfect combined task and planning problem. And you have to determine which tube to move first and which tube to move second. And then also automatically determine the graph and have to deal with the failures. Sorry. And then automatically generate the graphs and plan the motion between the grasps. And also, thanks to the human demonstration, we can set different goal patterns. For example, in the left part, we ask the robot to arrange the small tubes to the, blue area, and the long tubes to the red area. And in the red part, we ask the robot to separate them to two different sections, left and right sections of the tube rack. And then we just input the go pattern to the system, and then the system will do task level planning for the arranging sequence, and then do a motion level and grasp level and motion planning, motion level planning to generate the peak place motion. And I told our goal is to realize more complicated tasks. This is a challenge initialized by the Japanese government. And the goal is to assemble a bunch of metal mechanical objects like this. This one involves lots of pegging hole problems as well as bolt fastening tasks. And also you need to align the holes for the different pins. And
I don't want to interrupt you, but maybe you have 1 minute left or round out.
Thanks. So we solved the problem by developing a new hand, and we have 2 grippers in the hand, and the robot can do that. But we demonstrated that the robot could be able to do that using this hand. But we found that using the hand is difficult because we have to uninstall the previous robot hand and install the new hand again. Thus, instead of using a new hand, we developed a tool for the object, for the robot. The robot can use a tool like a human. It can regrasp the tool and move and use the tool to pick up objects. And in this way, we don't need to exchange the hand. Instead, we just prepare a bunch of tools, and the robot can use the tool to finish different tasks. And also here, I'm showing another tool which changes the gripping motion into a rotational motion. And then the robot can use the tool to fasten the bolts. Also, we can do human and robot motion collaboration. And you see in the previous video, asking a robot to fasten a bolt is very difficult. But robots are more advantageous in flipping or reorienting large objects. Thus, we ask the robot to reorient large objects and ask the human to fasten the bolts. The robot prepares the objects for the human, and the human just receive the well-posed objects and then directly do the fan motion. And together they improve the efficiency of each other. Okay, I guess this is the last one. And you can see in the previous video, a big problem were the cables. When we pick up something or when we manipulate the tool has a vacuum tube or electrical wires, which may get entangled with the object or destroy the environment. We follow the human, and we have 2 arms. We ask one of the arm to manipulate the cable and the other arm to manipulate the tool. Together, they can avoid the problems. They can avoid clearance of the cables. They can avoid entanglement with the robot hand. Okay, that's all of my talk. Thank you.